Needless to say, it's an incredible honor to speak at your seminar. Like I said, today I will be talking about deformation inequivalent symplectic structures and the Donaldson 4-6 question, and I'll tell you what that is, if you don't, I guess you haven't seen that before. And this is joint work with Amanda Hirschi. I guess the outline of the talk, I will first give you some background and history related to this question and symplectic structures. And then I'll tell you about our results. Then I'll give you the counterexamples we use and allude to the proof. Okay, so just to remind you, a symplectic form on a closed smooth four-manifold, well, okay, not necessarily closed. Smooth 2n manifold is a closed and non-degenerate two-form. And by deformation equivalent, I mean, so two symplectic structures, we call them deformation equivalent if you can find a diffeomorphism between the smooth manifolds such that the pullback of omega 2 has a path to your original omega 1. So I just require this path to be connected by all symplectic forms, no requirements on cohomology classes. Okay, so the question by Donaldson, as written in the Solomon book, this is where I learned it from, says, if I'm given two closed symplectic four-manifolds that are homeomorphic, then Donaldson asks whether they're diffeomorphic if and only if the product symplectic manifolds are deformation equivalent, where deformation equivalent is the notion I described right here. So this operation, I will call it a stabilization in this talk. I think people also called it stabilizations before. So this is I guess you can think of it as the corresponding operation we do to symplectic manifolds as opposed to the symplectic stabilizations in the smooth category. Okay. So some remarks about this question. Oh, feel free to interrupt me if you have questions. Some remarks about this question. So you may already be wondering why, if I have two non-diffeomorphic smooth four-manifold, when you cross them with, so let me say, x1, x2 is homeo, but not diffeo. Why do I know x cross s2 is diffeo to x2 cross s2? Because otherwise there's no point asking deformation equivalence. And so this part, when the question is stated, it doesn't really require simply connect. Well, they didn't mention simply connectedness, but I can only find how to prove it using simply connected manifolds. So by wall, two homeomorphic closed four manifolds are H cobordant, and then by Smale, once you're crossing it, you become six manifolds. Then you lie in the dimension that you can say, okay, two closed simply connected six manifolds are H cobordant, then they're diffeomorphic. So I guess if any of the audience knows whether this statement is true for not necessarily simply connected manifolds, I will be happy to hear. Okay. So that's the history. Oh, well, that's the background on the conjecture or the question. So now let me tell you a bit about what people have worked on. So in Ruan's paper in 94, he constructed homeo but not diffeo Kähler surfaces. So one of them is just CP2 blow up 8 times. And the other is the Barlow surface. So he showed that so these are non-diffeomorphic four manifolds. And he showed that when you take the product with S2, when you stabilize them, they remain non-deformation equivalent. Okay, so this is supporting the Donaldson question. And then in 97, in his paper with Ruan, Tian, they stated the stabilizing conjecture, which is exactly the Donaldson question restricted to the simply connected case. So they asked, as before, if you have two symplectic four manifolds that are homeomorphic, whether they're diffeomorphic if and only if the stabilized symplectic six manifolds are deformation equivalent. So this is shown in their paper. The stabilizing conjecture is shown for simply connected elliptic surfaces. And in Yolo Parker's paper, they also show that this conjecture is true for these simply connected elliptic surfaces using a slightly different method. And I want to note that both of them, they use Gromov-Witten invariants to distinguish the symplectic structures on the six manifolds. While in our paper, we use a more elementary invariant. That's the Hirschman class of the symplectic form that I will remind you of maybe in the next, in 2 slides. Okay, and then maybe in a different direction, Ivan Smith showed that given any integer greater or equal to 2, he constructs n symplectic structures whose first-gen classes have different divisibilities. I guess construct n symplectic structure on the same manifold. We call it Z, and this Z is simply connected as part of his construction. So in particular, his result would show that Donaldson's question, or the stabilizing conjecture, the stabilization by S2 cannot be replaced by T2. Sorry, don't know how to spell by T2. So this is because C1 of T2 will be 0, and if their four manifolds have different C1s, divisibilities of C1, then that will imply the six manifold will also have different divisibilities of C1. And the S2 case is a slightly more complicated, but that's the point of our paper. But it's not too much more complicated. So our result shows that, maybe I should pause on the, maybe there are some corrections of the history. I only learned from reading papers, so okay. So let me tell you about our results. So the main theorem, theorem A, we found infinitely many closed smooth four manifolds, each emitting deformation inequivalent symplectic forms, omega-1 and omega-2, such that when you stabilize them, the six manifolds are still symplectic deformation inequivalent. And so in particular, this will be a counterexample to the Donaldson 4-6 question in the forward direction. So we have diffeomorphic manifold such that when you stabilize them, the symplectic structure are non-deformation equivalent. And a remark is that we actually give 2 types of examples in theorem A. One is the McMullen-Tubbs example. So these examples all exist in the literature already. I guess the point is to show that they remain like, so the examples are four dimensions, and the point of our paper is to show that they are still non-deformation equivalent in the six manifolds. So okay, so the first one is by McMullen-Tubbs. And the second one is the Smith example that I mentioned before. And this one, like I said before, it's also simply connected. So it gives a counterexample to the stabilizing conjecture also. And once you have that, one stabilization is not enough to, I guess, make your forms deformation equivalent, you might ask, can I do more stabilization so that my forms become stabilization equivalent? And our theorem B says, no, you can. In our examples, you cannot. These examples in theorem A remain non-deformation equivalent when you stabilize with more copies of S2. Okay, so let me tell you a bit about the strategy. So this is the nicest, the most natural thing you can, most natural strategy you can think of. So you just first find examples of a fixed smooth manifold that emits different deformation equivalent symplectic structures. Then you show when you stabilize. So like this is the stabilization construction that I keep referring to, that you direct sum with the standard symplectic form, that they are still non-deformation equivalent. And as mentioned before, the invariant we use is first Chen class. So given a symplectic form, I can associate a compatible J. Okay, so this is very classical, but just to mention here for completeness. And then, so once I have a J, I have a complex bundle, and then I can take the first Chen class of this. And note that any compatible J's are homotopic, so this is a symplectic deformation invariant. Now the goal is to show, it will be sufficient if I can show C1 of X S2, omega 1, omega standard on S2, and C1 of X cross S2, the second form stabilized with the standard form on S2, lying different orbits of the action of diffeomorphism on of diffeomorphism of X cross S2, like the diffeomorphism on the six-manifold. Okay, so this is the invariant that we use. And before I go into some perhaps more abstract definitions, let me give you a bit even more motivations. So we emphasize that before us, there are already examples of closed smooth four-manifolds admitting symplectic structures that lie in different orbits of, whose C1s lie in different orbits of diff, but this is diff of the four-manifolds. And in fact, we do use those examples. And the difficult part is to go from four dimension to six dimension. Okay, I forgot whether in the conjecture I stated but yeah, we're only looking at four manifolds stabilized to six manifolds, and that was where the conjecture was stated. Sorry if I missed the dimension in my statement of the conjecture. Okay, so how do we go from 4 to 6? So notice that we will be done if our diffeo on the six-manifold X cross S2 splits. So this would mean that if you look at the action of diffeo on C1, so C1 of, I guess, X cross S2, and omitting the symplectic forms. So this will be C1 of X sum C1 of omega. If the diffeomorphism kind of split these two parts of the cohomology, then you'll be done. But that's not always true for diffeomorphism on the product. So what we want to do is we want to constrain an arbitrary diffeomorphism of X cross S2 can act on H upper 2 of X cross S2. Then I hope the strategy is clear. So this would lead to a very natural definition, which is the following. Given two spaces X and Y, we define G sub XY to be the set of homology equivalences. So this means that maps that induce isomorphisms cohomology. So maybe we should have called it the cohomology equivalences. But anyway, so we want we define GXY to be the set of homology equivalences of X and Y such that it preserves the second cohomology of the first vector. So maps H upper 2 X Z to itself. And in addition, the projection map Y is also a homology equivalence. For each Y in Y. So we don't know that our diffeomorphism will be splitting, but we want to define a sufficiently general set of maps so that we still see the product structure of the manifold that we're considering. And furthermore, we can see we can find a H group in our GXY to be the H group of homotopy equivalences. So this is the same definition as here. You just replace all the homology equivalents with homotopy equivalences. Okay, so the good thing is that both types of our examples have their diffeomorphisms satisfying the above algebraic conditions, meaning that any diffeomorphism will lie in either xy or gxy tilde. So I mean, we need to prove this, but this is the nice feature. Of our examples. So with this in mind, let's reconvene and see what the steps we need to do to prove our theorem A. The first step is to find a smooth four-manifold with symplectic forms omega-1 and omega-2, such that there are C1s lying in different orbits of diff of the four-manifold. And then we show that C1, and then we show that if C1 of the four manifolds lie in different orbits of homology or homotopy equivalences, then C1 of the stabilized six manifolds also lie in different orbits of these H groups that we just defined. And then lastly, we want to show that any diffeos of our specific examples, X cross S2, they lie in these H groups. Okay. So now I will spend more time on this step. And then I guess the order is I'll first spend more time on this step, and then I'll show you the examples, and then I'll give you the proof. Okay. Okay, so the first step, this is, you can think of this as an algebraic sufficient condition. So the essential part is this proposition. We let X be a closed, smooth four-manifold with symplectic forms. Oh, actually, I don't think this one depends on dimensions, but yeah, let me just say, given an X, which is smooth four-manifold with two symplectic forms, omega-1 and omega-2, if we suppose their C1s are in different orbits of actions of homology or homotopy equivalences of X on H over 2 of X, then I guess you can guess where I'm going. Then the stabilized symplectic structures have their C1s standard lie in different orbits of g, x, y, or g tilde x, y, depending on which examples are in, whether it's homology equivalence or homotopy equivalences that you can use. Okay, so let's see a proof of this proposition. The proof is very elementary, so I will give you a full proof. Okay, so let's suppose for the contradiction that you have a map in GX_S2. So this means, to remind you, that this map is a homology equivalence B maps H upper 2, so the pullback of it maps H upper 2 of X to itself, and C, the projection to the first coordinate is a homology equivalence. Okay, so let's suppose for the contradiction that we have a psi that pulls back one of the that pulls back C1 of one to C1 of the other. Then psi of H is H plus, so what is H? Sorry, H is, okay, depending on your, what you do, I guess. So this is a second homology class of S2, and this is the unique generator there. You can think of it as Poincare dual of the point, or the algebraic dual of S2, or you can think of it as the C1 of the hyperplane line bundle. One. So I want to see where psi star pulls back H2. So this is equal to H plus alpha, where alpha is some cohomology class in X. So it can mix the cohomology class. Because it's a homology equivalence, I know this is the coefficient here is plus minus H, and a combination of B and this assumption tells you it's actually 1 plus 1. So I'll just ignore. There's no coefficient here. So once you have this, and then you observe that the pullback of H2, H square is 0 because it's a fourth cohomology class. So then you just expand. So sorry, this equals to square plus 2 alpha H plus alpha square. This equal to 0. And then recall that the cohomology of your X cross P1 is just a cohomology ring of X adjoint H mod H square. So this tells us that 2 alpha is 0 because this is a coefficient. Sorry if this is too elementary, but the whole paper is just kind of algebraic topology. So I'll give you a sample proof. So okay, so now by the assumption, together with the fact that C1 of P1 with omega standard is equal to 2H, we know that C1 of omega 1 plus 2H is equal to psi pulls back C1 of omega 2 plus 2 psi H. So again, we're using this assumption. And this is equal to psi C1 omega 2 plus 2H plus 2 alpha. And then we know this is 0. This is what we just proved. So this gives us C1 of omega 1 is equal to psi C1 of omega 2. So this is nice, but this is a map on the six-manifold. and we want to map on the four-manifold, so we just define psi hat to be the projection of the first vector of psi star psi. And then since we know by assumption that psi is in GXY, psi preserves H upper 2 of X Z. So this gives us that psi hat of C1 of omega equals to psi, pull back C1 of omega 2. And now we can use this to tell us C1 omega 1. Okay, so this is a contradiction because we assume that on the four-manifold level, these cannot lie in the same orbit of homology equivalence. Okay, so this is the algebraic sufficient condition, sufficient only just for our examples. And now let me tell you a bit more about our counterexamples. Okay, maybe before that, I don't know if people have questions on this proposition. Okay, we'll continue. So our counterexamples, let me tell you about the first one, which is the one by Smith, Ivan Smith. So he considers a fiber sum of T4 with this symplectic form with 5 copies of E1. I mean, this is a specific construction. His construction works for this 5 can go to N, and then you have more different symplectic structures, but I'll just focus on this case. So what he did is that he fiber summed T4 with 5 copies of E1 along the tori Tx, Ty, Tz, and 2 copies of Tw. So you can check that Tx and Ty are symplectic, while Ty, Tz are Lagrangians. So for the Lagrangian ones, we need to perturb in order to do the fiber sum. And then he actually uses the different perturbations. So, okay, so what does that mean? So on a Lagrangian torus, you can perturb the symplectic form to be the error form on your Lagrangian, and you can either pick the perturbation so that it's a positive or negative error form. So the symplectic structures he constructed is based on this different perturbations. So let me tell you what he actually stated. So he showed that the simply connected manifold Z, so this one, emits 2 deformation inequivalent symplectic structures. And in fact, there's omega plus and omega minus. So this is the perturbation. This is symplectic structure obtained by perturbation so that the symplectic forms are all agreeing with the orientation of your tori, and omega minus is obtained by the perturbation so that it disagrees with Tc. But anyway, so these are symplectic structures so that they have different divisibilities. In fact, 3 divides the first one, while the second one is prime. Okay, so this is his examples. And our job is just to see that when you stabilize them, they're still deformation equivalent. So Z is his example, and we're stabilizing with S2. And just again. Okay, so how do you prove that? We know that the first Pontryagin class, when you evaluate with the fundamental class, it's non-zero. This is just a calculation. So then we can compute P1 of our stabilized manifold, which is also non-zero. S2. So now we recall that diffeomorphisms preserve the first Pontryagin classes up to sign. So I mean, we actually allow diffeomorphisms to be orientation reversing. But anyway, and then together with this fact that diffeomorphism preserves P1 and the fact that our homology is just so simple, it's free, we know that any diffeo of Z cross S2 must satisfy, must send the fundamental class of S2 to S2 of plus minus, sorry, because it preserves, because this is a computation here. Okay, now given any alpha in H over 2 of Z, we have that the pullback of alpha is equal to alpha prime plus some AH, where alpha prime is just some cohomology class in Z and A is some integer. So we really want to say that our psi will lie in one of the gxy or g tilde xy's that we saw before, because then we satisfy the sufficient condition. So, okay, how do you show that? You just want to show this A is 0. So okay, this is again like a just algebra topology exercise, but you can compute this to be S2 because we already saw this. So this is how you see this equality. And then this is equal to psi push forward of psi pullback of alpha cap with the S2 class. And then this is, you just compute this. So this will be A times S2. And this will give you that our A is actually 0. So this tells us psi pullback preserves H over 2. Now, similarly, not similarly, in order to satisfy all parts of the definition of GXY, we also need to check that the projection is a homology equivalence. So to see this, you define, okay, you define psi hat again to be the projection of the first coordinate. Then we recall since psi preserves S2 up to psi, this is what we showed before, psi hat has degree 1, plus minus 1. Then again, by algebraic topology computation, for any classes alpha beta that are in H upper 2 of Z, this is equal to plus minus alpha times beta. Okay, so you can see that psi hat is actually a homology equivalence by considering the intersection form, for example. Okay, so this shows us that psi is in G, Z, S2, and then by the sufficient condition above, we're done. We have that. The six manifolds have like the stabilized symplectic structures are non-deformation equivalent. Okay, so the remark is that this argument actually can be generalized to stabilizing with other Riemann surfaces also arbitrarily many times. The algebraic topology gets a little trickier, but it's essentially the same argument. Okay. Any questions for Ivan Smith's example?
Yeah, I mean, I have a question. So, I mean, is there a reason? I mean, he's using this 5 times, this 5 fiber summing. So, is it like possible to do it more, maybe?
Oh yeah, I prepared it before, but then I didn't know how interesting that would be for people. But let me give you a quick outline. Sorry to be scrolling. So his argument is that so you have right. So he defined. So okay, let me just go from the start. Given L Lagrangian, this is what I said, one could perturb the ambient omega by a small amount. So omega is non-vanishing area form on L, and then this perturbation can either be positive or negative. agreeing or disagreeing. And now suppose, okay, now this is just the usual fiber sum. Maybe I will skip, like you can identify the neighborhood of the T2. And then the point is that okay, so there are 2 points. One point is that the diffeotype only depends on the smooth structure on this is completely determined by the orientation of T. So that's important that we have a single smooth type for our four-manifold, because otherwise, and we want to give a counterexample to the Donaldson conjecture. So this you can show. Okay, you can see his argument is not too difficult. And the second point, so this is the first point. The second point is that you have a formula for C1 of fiber sum. And when you do a negative perturbation, so this is just a usual fiber sum first-term class, you write it as C1 of the left side, of the right side, and then you look at the Poincare dual of, you need to be a little careful where you're taking your cohomology classes, but let's say you agree with me, this is the formula. And then you just compute C1 of the plus form and C1 of the minus form. So plus form, like I said, was obtained by all orientation agreeing with the existing orientation on all your tori. And then the minus is obtained such that you choose the perturbation of TZ to be negatively oriented. To induce the symplectic form that's negatively oriented, that disagrees with the orientation on TZ. Okay, then you do the computation based on this thing I assumed. Then one of them, so C1 of T4 is just 0, and you just look at, this is the right-hand side, and then you minus 2 of, maybe one thing I didn't tell you is TW is equal to TX plus TY plus TZ plus, that's it. So if you compute the plus form, you will get minus TX minus TY minus TZ minus 2 TW. So this is 3 minus 3 TW. So it divides, 3 divides it. And on the other hand, if your perturbation is the negative, then by some assumptions, you don't need any assumption to get this form, but then by some assumptions on the cohomology class of TZ, you will see that this one is prime.
Okay.
So this is his proof, Ivan's proof.
I mean, you can get lots of examples like this, right? That he constructs. I mean, using as not just T4, but you could also use other product surfaces as well to, like sigma G cross, let's say sigma G cross T2.
Yeah, I think so. I think there could be many examples, but I'm not an expert, so I guess we just found. So this is one type of examples, and let me go back to the talk. Thanks for your question. So the next type of example is the McMullen-Taubes example. So we actually, so McMullen-Taubes in their 99 paper, they have 2 types of example. One of them is simply connected, which people, then over there, the C1s are differentiated by Sever-Witten invariants. But we're actually looking at their simpler example, which is just a double branch cover. So let me go through the examples. So this one is like actually different from Ivan's example, at least on a glance. So you consider the 3-manifold that's T3 minus a link, and this is isomorphic to, you can find a diffeomorphism between these three manifolds. It's not easy to see, but this is induced from the zero surgery of the Borromean ring, Borromean link in S3. So you can see that these two are, and let me say homeomorphic, where L is the 3 S1 factors, the geodesics of the 3 factors, and then L4 is just any representative so that it lies in this class, and K is a Borromean ring. Okay, how I want to construct this manifold N is that N is a double branch cover of your T3 over L, this L, associated to the homomorphism that maps your meridians, the first three meridians to just 1, and then the fourth one to be -1. And in particular, this N has a fibration over S1. So this is a three-manifold. You have a fibration over S1 induced by the fibration of T3 over S1 because you're doing double branch cover over a link that's transverse to all your fibers of T3, which is T2. So you have this fibration, and then recall that the Euler class of a fibration only depends on the homology class of this d rho, the derivative. So it might be a little weird that my Euler class is the H lower one, but this is how they discuss things. So it's defined to be the zeros of a generic section of your three-manifold down to the kernel of your d rho. Okay, and the important thing is that this Euler class of a fibration is related to the first term class of the four-manifold X cross N cross S1. So let me go through their lemma. So that these two theorems are, well, lemmas are embedded somewhere in their paper, but let me summarize them here. So they prove that there exists alpha 1 and alpha 2 induced by submersions, such that E alpha 1 and E alpha 2 lie in different orbits of alt pi 1 on your first homology. And furthermore, if you consider the four-manifold, which is obtained by the three-manifold cross S1, to each alpha that's represented by a differential of a fibration, so in particular, it's a submersion, you can associate an S1 invariant symplectic form. So that, I mean, you can write it explicitly, and then you can compute its C1, which is a Poincare dual of X of this Euler class times S1, where this S1 is this S1 factor. Okay, so you already see as a corollary that if you have for any homotopy equivalence phi on X, we have that for the given E1, alpha 1 and alpha 2 given by Molin-Taubes, you cannot map one of them to the other. And in particular, the C1s cannot be related to each other under a homotopy equivalence. So yeah, so
yeah, there is a generalization of, I think, the Taubes work by Vidusi. I think he does it like for many. Stefano Vidusi, maybe, I don't know if you've seen his paper. I mean, he gets actually many like symplectic, I think, so not deformation equivalent symplectic classes. So this is due to, I think
right. Yes.
So maybe that might be useful for you. I mean, so that is like his work. I mean, coming after Taubes, yeah.
Yeah, I think we wanted to say something there, but there was a yeah, I guess there, I'm not sure if he computed, but maybe we can, I can think about
Okay, yes, I don't want to interrupt. Yes, yeah.
Yeah, thank you. Okay, let me finish the proof, which is, I think, almost done. Yeah, this is the last page. So it's just very nice that this X cross S, N cross S1 in Taubes paper, Macmillan-Taubes paper, it's aspherical. Well, this uses the fact that we have a S1 invariant symplectic structure. Okay, maybe let me tell you aspherical to remind you, it's just the universal cover is contractible. Yeah, okay. Indeed. So now we're ready to show why X gives us counterexamples as well. So as well, different from before, where we use the fact that diffeo preserves P1, here we use diffeo preserves. Okay, I guess you'll see. So now we have pi 2 of X cross C1, which is equal to pi 2 of C1, just CP1, because X is aspherical. And then we assumed, okay, maybe I should say psi is in diff of x cross p1. And we see that this induces an isomorphism. And since the Hurwitz homomorphism is functorial, we see that the homology classes are also mapped to each other up to signs. Okay, this is a similar argument as before. If it preserves the homology class, then it preserves its annihilator, which is h upper 2 of x in this case, because we're considering the manifold x cross p1. And then you define a similar thing that's a projection map. And then so now we're left to see that psi hat is a homotopy equivalence. And you can see that because of how simple our manifolds are, pi1 of x is just equal to pi1 of x cross p1. So this is a homotopy equivalent, a weak homotopy equivalence. So it's a homotopy equivalence because of CW. Anyway, so our psi lies in G tilde, and then we can apply the sufficient condition again to obtain that our this x cross S2 has non-deformation equivalent symplectic forms. Okay, sorry. That's it. I think I was actually a little early.
That's cool, yeah.
Thanks for the questions. Oh yeah, maybe more questions.
Any question?
So can you construct simply connected examples? Seems harder.
Besides Ivan's examples.
So his examples